Okay, so without much delay, let's begin. Um, Good evening to all. So, this is our last interactive session for the course Foundation Engineering, which is taken by Professor Kousik Deb as part of NPTEL online courses. So, I am one of the TAs, AS Kashyap Vasudevan. Uh, we will be discussing a few questions which is based on the contents discussed in the last week 12. So this is going to be the last interactive session. I would really like if you would interact more. And as we all know, the exam will be on October 29th. So whoever has applied for the exam, all the best. So okay, so without much delay, let's start. uh, as usual, let's have a small recap about the contents about the in the last week. So this is the concluding week. So 2 3 concepts were discussed. So one of them being so as continuation from the last week 11, analysis of cantilever sheet piles on cohesive soil was discussed, and the differences, the bending moments and the forces, lateral forces acting on the sheet piles were analyzed. And after that, the alternative. So whenever in our design, if we are getting the embedment length as too high, that is our depth d, whenever it is too high, we need to go for some alternative, that is anchored sheet pile. So anchored sheet pile will increase the resistance of the sheet pile, and the embedment length requirement will be lesser after we introduce anchor. So what the idea is, we are connecting the top portion, in a suitable depth, top portion of the sheet piles into the backfill beyond our failure plane, so that we get more resistance against the failure. Okay, so both in like for anchored sheet pile, both granular soil backfill and cohesive soils were discussed using the free earth method. There is some other method called fixed earth method that was not discussed in this course. So that's beyond the scope. So after that, we moved on to some example problems on anchor sheet pile, and then came the braced excavation. So braced excavation is something very important in field, especially during construction. So the idea is, whenever we have something, whenever we are doing an excavation, we need to support the backfill appropriately to avoid accidents and losses. In order to do that, we need to give sufficient protection for the backfill. So sometimes this sheet pile will not be enough, and it won't be fast enough. So brace excavation is a alternative for faster and better support of the backfill, especially when there is a very narrow excavation, and when we have two backfills in the opposite. This is useful for all the different constructions, like underground tunnels, or stations, or underground whenever we are doing excavation for footings. So all these cases, we need some support. So braced excavation is another option. So after that, how to but whenever we are going for braced excavation, we should know what is the pressure acting on this braces, and the sheet piles, and the beam systems which is comprising these braces, and so that we can give appropriate sections for the beam. For example, we have something called whale beam, and we have different sheet piles. So to select, as a designer, to select the appropriate cross section for these members, we should know the loads acting on it, and the highest load or bending moments acting on these members. Okay, hence we solved a few problems on beam-based expression. We will be solving one of them in this session, and then we moved on to another concept of underground conduit. Underground conduit is nothing but when we have a pipeline, or a tunnel, or something which is underground. So that we should know what is the vertical pressure acting on it, so that we can design the section appropriately. So it could be water supply lines, sewage lines, or it could be cross drains or anything like that. So in all these things, we should know the overburden pressure or the vertical pressure acting on the roof of the conduits and all. So a few problems were discussed on that. And when we say conduits, we have like generally four types underground conduits. So I could say first one being ditch conduit. So in ditch conduit, it's nothing but we excavate a ditch and we lay our conduit and we fill the ditch bag with the backfill and we compact it appropriately. So that is ditch conduit. In second one is positive projecting conduit. Positive projecting conduit is nothing but when we have a natural ground layer, we will embed our conduit slightly into the ground layer in natural ground, and we will establish. We will install a embankment over it. So these are generally done in highway cross drains or railway cross drains. Uh, Ditch conduits are more suitable for smaller things like sewers or water lines, etc. This is generally done for cross trains and railway for highways or railways, etc. So third one is to avoid much of the lateral earth pressures on the conduits. We can also go for negative projecting conduits. Negative projecting conduits. It's very similar to positive projecting conduit. The only difference is our conduit is inside the natural ground level after excavation of a ditch, and above the natural ground level again we are constructing our embankment. So that is the only difference. But in this case, lateral earth pressure will be much lesser when compared to positive conduits. Then apart from that, next one is imperfect projecting conduits. This is a special case. So here we are above the conduit. We are giving a space for granular material so that the overburden pressure is less. Arching can happen. So whenever we are talking about underground conduits, arching is an important thing. So soil arching is nothing but what happens is this is a phenomena where our whenever as we go deeper, till now simplistically we have been taking as a triangle, but soil due to soil arching as we go deeper and deeper from the natural ground level, the lateral earth pressure will stop increasing beyond some depth, and uh, we need not if we are giving this the same simplistic design, we will end up overestimating our cross sections, which is not economical. So we can take this to our advantage. What happens is there is a transfer of pressure between the yielding and unyielding soil mass. So basically what is happening is, especially for this conduits and all, we have a soil portion which is yielding. So for example, whenever we have a conduit and we have a backfill over it, so this portion of the soil is trying to settle down, and we have other soil material here, so this will give some resistance. So from that for a larger depth, this causes soil arching. So our conduit is experiencing a lesser effective horizontal stresses, so lateral stresses. So that is one advantage. So whenever we are saying about soil arching, there are two kinds: active and passive soil arching. In active soil arching, the structure is compressible than the surrounding soil. This is where we have lesser pressures acting on the conduits or whatever structure we have when with respect to the surrounding soil. Passive soil arching is nothing but the opposite. Here the structure is stronger, and the surrounding soil is weaker, so there are more stresses on the uh, structure. So in active we have more advantage when it comes to lateral earth pressure, reduction of lateral earth pressure. Having said that, so we ended the week mm, by conducting the analysis of loads on conduits. So we found a way to calculate the vertical stresses on a tunnel or a conduit. So we will also solve the problem related to that. Okay, yeah. So let's move on to the problems. Um, the first problem, in this problem, we are dealing with the braced excavation. So here we have depth of excavation of 10 meter. So let me label it. So this is 10 meter, and it is said that four stress struts are there. So let me number it as 1, 2, 3, and 4. And the horizontal spacing, that is SV, horizontal spacing is 2 meter, and vertical spacing between first and second is 3 meter, and second and third is 3 meters. So this is 3 and this is 3, and between the third and fourth strut is 2 meters. So this is 2, and the first strut is 2 meter below the ground line. So if I'm writing, this is also 2. Okay. Use appropriate pressure distribution based on gamma h by cu value. So we need to find gamma h c value, compute the maximum value of total strut force. So we have four struts, and it will be having some compressive loads, as we can imagine. So there is some loads in this. Sorry, it should be the other way. So we should know what is the load, so that we can during the excavation itself we have to we must have the appropriate cross section area required. So in order to decide that, we should know this forces, strut forces. So let us see. So whenever we say about braced excavation, we should know about the lateral earth pressure profile. So in the braced cuts, we have three different cases. First is sand. So when we are talking about sand, we can take it as a rectangular lateral earth pressure distribution. So we can, it's so simple, we can calculate the load directly. So the value of this is given as 0.65 gamma h tan square 45 minus 5 by 2. So these formulas are obtained using different lot of research and experience. So that we can quickly in the field we can quickly come up with the section requirements of the structure. So this is for sand. We are taking it as a rectangle, and this is for the next case is two cases are for clay. Within clay we have two cases where gamma h by c is less than 4 or gamma h by c is greater than 4. So in both the cases we have slightly different profiles, and the maximum pressure, lateral pressure, is also different for both the cases. So here, this is what we are. I was trying to say before, because we would have taken uh, a different profile generally, a triangular one, but we would end up overestimating the profile. So we need not do this. That's why the soil arching is to our advantage. Okay, so let us see what our particular case is. In our particular case, we have C as Cu is given and gamma is given. H we know it as 10. So let me find out what is gamma H by Cu. Gamma H by Cu is 17.5 into 10 divided by 35. So if I find out this, I will get it as 5. So this is obviously greater than 4. So we have to go for this profile. That is we have a trapezoid. Okay, so uh, and what will be the base? So let us see the base. So base pressure at base is equal to gamma h minus 4c. It is gamma h minus 4c. So when I say gamma h minus 4c, we have 17.5 into 10 minus 4 into 35. So this value is 52 point, sorry, not 52.5. This value is 35. So we have the base also. We know the base of the area is 35 kPa. Now we know this distance also. This is 10, so this, I can take it as 25 2.5 meter, and this will be 7.5 meter. Since the whole depth of the excavation is 10 meter. So I have the profile. I can go for it now. You can also try, since our phi value, this five is in a real life scenario, if this particular problem in the field, uh, 5, since the 5 is very near to 4, you may also take this particular case, and you might end up with a different, maybe a larger force also. So for being a safe design, you can also go for this uh, this value, for example this value, that is 0.2 to 0.4 gamma h, but the profile you can keep it as same. That is what sir has done in the video. But for the sake of this question, we can take greater than 4, so there is no issue. uh, okay, so how will the profile look like? So we have 35 kPa at the bottom, and this is 7.5 meter, and this is 2.5 meter. So if I am measuring it from here, we have 7.5 and 2.5. Okay, so this is also 35 kPa. And if, let us say, if I'm taking the load, so it will act as a point load. Our braces, so our struts are exerting a load on this soil, so that will be these forces. So if I can take also like this, so these are the forces we need to calculate. So if we can calculate these forces, we can easily design the braces, right? So let us say this is R1. So this is the first one, second one, third one, and fourth one. We have four braces, four struts to be more correct. And at that particular level, we can assume a load which is acting on the soil. So these are the four loads that should resist. So let me name it as R1, R2, R3, and R4. So these forces to reduce this lateral air pressure, right? So let us say we have a lateral air pressure like this, P or whatever. Uh, what can be done is, uh, we can hypothesize this as a beam. So we have a sheet pile here actually. So just inverting this figure, we can take it as a four supported beam, and with four supports, and we can find the all the four supports by separating the load, uh, assuming assuming that this is a flexural member, this sheet pile, and this struct as it acts as a load. Okay, or a support. Structs acts as supports. Okay, so if we are doing that, we will get let us say this is R1. Sorry, this is still 2.5 meter, and this is still 7.5 meter. The same thing that is there in the previous figure. I'm just tilting the thing by 90 degree. uh, I'm just tilting this figure anti-clockwise by 90 degree. If I do that, I'll get this. So I can write it as here R1. So this is just 2 meter, and I can write R2, R3, and R4. So this is 3 meter, 3 meter, and 2 meter. So I can hypothesize this as a load. So this will be like loads, UVL and a UDL we have, and the magnitude of this load is 35 kP. Or if you are taking per meter, we can also take it as kilonewton per meter, because if you are considering 1 meter length. So we have 35. Okay, so that's it. So I'm going to break this into three different spans. So we have three spans, 1, 2, and 3, one being overhanging. So I will this split it into three spans, that is R1, R2 dash, and this will be R2 double dash, and this will be R3 dash, and this will be R3 double dash, and this will be R4. So I'm splitting the same thing into three different spans. So the loading will be like this, and it's quite simplistic for the second and third spans. Uh, okay, so let us say this is 35 kPa, kilonewton per meter. Now, what will be our forces? So just looking at the first figure, so looking at the span 1, I can take moment with respect to this point. So at the R2 support, I can take the moment. So we know that this distance is 3 meter, and this is 2 meter, and this is 2.5 meter, and so the rest will be 1.5 meter. Okay, so sorry, not 1.5, it will be 2.5. Okay, so let's just find out R1. So if I'm taking moment with respect to the support R2, I will get R1 into 3 is equal to half into base, that is 2.5, into height. I'm talking about the triangle we have. So area of the triangle will give me the load. So okay, let me write this properly. 2.5, this is the base, that is base of the triangle, into 35, that is the height. So we have the load. Now we need the moment. So our load is somewhere at the centroid, the total load. So we need the moment into, we have to take the distance. So 2.5 plus, that is this distance, ha, one third of this 2.5. So 2.5 by 3. This is the moment due to this triangular load, and if you want the rectangular load, plus 2.5 into 35, that is the total load, into distance is 2.5 by 2. So if you solve this, you will get R1 is equal to 85.07 kilometer. Similarly, for span 2, okay, for span 2 we have R, okay, excuse me, okay, so in order to get, so before we go to span 2, R2 dash, R2 to a single dash. So R2 dash is equal to the total load. The total load is half into 2.5 into 35 plus 2.5 into 35 minus 85 0.07, that is our R1. This will be equal to, we can find R1 like that. That will be equal to 45.18. Let me just confirm that. So, sorry, it's 46.18. So, R2 dash we have. Now, for span 2, it's very simple. It's UDL. So, throughout the length, it's the same. So, we can divide it by half. Remember, this analysis is very simplistic. We are assuming a lot of things. We cannot just split these beams like that. But it's fine. So in the second span, we have R2 dash and R3 dash. We can just divide it by 2. So the total load is R2 dash will be equal to R2 double dash will be equal to R3 dash. Just it's symmetrical, so since it is symmetric, I will take the total load and I will divide it by 2. So total load is area of this thing, that is our span is 3 meter, so uh, it will be 3 into 35 by 2. So 3 into 35 that is 52.5 kilometer. So we have got R3 dash and R2 dash, R2 double dash. For span 3, that is our last one. It's also very simplistic. So we can take R3 double dash is equal to R4 is equal to, this is 2 meter. So 2 into 35 by 2. That will be 35 kilometer. So we have everything. We can get this our real R1, R2, R3. So our real R1, R2, R3 will be, so R1 is equal to 85.07. R2 is equal to R2 dash plus R2 double dash, that is 46.18 plus 52.5, that is like 90, 46, 6.18 plus 52.5, that is like 98.68. Let me write it properly. 96.98 point, sorry, 98.68 kilometer. So R3 is equal to R3 dash plus R3 double dash, that is 52.5 plus 35, that turns out to be 87.5 kilometer, and R4 is equal to 35. So we know all the loads. So the question is, if we know all the loads, what is the forces on the strut? So here we are missing a small point, that is our horizontal spacing of the strut is 2 meter. So when our horizontal spacing is 2 meter, we have been taking all these loads for 1 meter. So the forces on our each strut is double, because in the plan it will look like this, will look like this. We have one strut and we have another strut. So if the plan, if you are looking from the top at both the backfills, uh, if this is 2 meter, and similarly we have the next one like this is also 2 meter. So our this particular strut will take, this length is 2 meter, so it will take double the load. So I have to double it to get the total force. So the total uh, strut strut force for strut 1 is equal to R1 into 2, that is 85.07 into 2, that is 170.14. Similarly, total struct force for struct 2 is equal to R2 into 2, because our spacing it's dealing with the 2 meters of the in the horizontal, in the direction plane to the surface, so surface of a paper. So it we have to consider the two, both the 2 meters, because the pressure is acting on the those 2 meters. So our single struct has to resist the 2 meter width of the slice. So we have to multiply by 2. So that is our R2 was how much, 90, R2 is 98.68, 98.68 into 2, that is 197.36 kilometer. Total struct force for struct 3 is R3 into 2, that is 87.5 into 2, that is 175 kilometer. Similarly, the struct force for fourth one, that is R4 into 2, is uh, 35 into 2, that is 70 kilometer. So we have the struct forces. So now we can say, as a geotechnical engineer, we can tell the contractor that we need a strut that can resist compressive force of the highest one. We can choose the highest one, that is 97. So we are supposed to get 97. So this is the nearest answer. So the biggest value we are supposed to, so strut 2 at least we should give a member that can resist the compressive force of 197. The next question is, what is the maximum acting beam? So in the we have a continuation question, the braced excavation detail in the problem one. What would be the maximum moment in the beam? So if this is the braced excavation we are talking about, we have something called whale beam. So we have sheet piles here, and these sheet piles are supported by our struct, but the struct is landing on the whale beam. So whale beam, we are in this question we are asking maximum moment of the beam. So that this beam their mean is whale beam. So we have to look it at as a plan. So if we have this sheet pile like this and soil, and we have a whale beam which is resisting, so this load is resisting 2 meter span thing, and we are supposed to find the moment. So maximum moment is given as RSH square by 8. It's nothing but the bending moment of a single load. So if we have a single load and we need a bending moment at the maximum bending moment, we can also hypothesize that like this, R by 2, assuming that it's a simply supported beam, the maximum moment will be at the middle. So I can take it as R by 2 into L by 2. Oh, sorry, not this one. Uh, so okay, sorry. So this is the formula for finding the maximum bending moment for a particular whale beam. So whale beam. So in this case, our maximum is R2 maximum is 98.68. So we are supposed to take that. So here 98.68 into SH square. That is our SH square is our horizontal spacing. So this value will turn out to be 98.68. This is nothing but 49.34. that is this way. So that's how it is. Now this is quite straightforward, so this is nothing much about it, but here there is one more issue actually. We are we need something called sheet pile is also a bending member. So sheet piles bending capacity is also a question. So when we are calculating the strength required for a sheet pile for a particular excavation, we should know what is the bending moment acting on it. So we are also supposed to find the bending moment of the sheet pile required. So we know that bending moment will be maximum wherever we have shear force as zero. We'll just as a continuation for the question, we'll try to find the maximum bending moment in the wall or the sheet pile, nothing but the sheet pile. So in order to get this, we have actually since our beam is like this and we have a load something like this, our SFD will be, it will keep on, sorry, our SFD will be like this. So we have a section in between support 1 and 2, that is R1 and R2, where our SF shear force is 0. So this is the point where we'll have maximum bending moment. So just to analyze that, so we have R1 and R2. There is a place between R1 and R2 where our shear force is 0. So we can find out that directly, the position. So let us say this is X. So we know that this is 2 meter and this is 2.5 meter. So we can directly find the position where the shear force is 0. That is this particular point. So to find that particular point, we can take like to locate us. So shear force is 0. So at X, let us say this section, at section X. So this is 35. This is 35 kilonewton. So at X shear force, let us say shear force is 0. So in that case we know that R1 is 85.07. So I can say 85.07 into, so first let us locate the section. So this is the force acting in the, so let me take force acting in the right side as towards the right side as positive. So I'll take this as positive and 87.07 minus the other forces. So I have a triangle and a small piece of rectangle. So triangular piece, the base is 2.5. So half into base into height minus this small rectangle. So this rectangle. This rectangle's width is x minus 2.5 and into the 35. So this should be 0. So our shear force at this section is 0. So I am finding the shear force. So the forces moving towards right is taken as positive, and the whichever sign convention you take, you will get the same answer. So x will, if you solve this, x will turn out to be 3.68. So we know the location. Now we can find the bending moment at this location. So bending moment at x is equal to 3.68 is maximum. So let me write it as m max. So let us say the first. So we have this as 3.68. So let me say R1. So R1 into the distance. So let us say 85.07 into 3.68 minus 2. So that is this distance. This distance is nothing but the total distance 3.68 minus 2 plus, sorry, so this was in clockwise direction. So I am taking clockwise direction as positive. We can take the other way also. So let me take the clockwise as negative. So the other positive So that is half into base into height, that is our triangle. So we know the force of the triangle into distance. So this distance is let me say, so 3 points, let me write it as 3.68, that is total distance, minus so this is our centroid. So our centroid is located at a distance of 2 by 3. So this particular distance is 2 by 3 of our 2.5. So 2 by 3 of 2.5 plus, we have a rectangle now. So the rectangle's width is 3.68, sorry, so 3.68 minus 2.5 into 35, or let me write the other way, uh, 35 into 3.68 minus 2.5 into, so this is the force, this is the force, and this is nothing but half of this width. So I can write it as again into divided by 2. So there are 233.68 minus 2.5. If you solve this, you will get something like uh, 30.47 kilometer meter. So I can say to the like I can say I can select the sheet pile wall of section that can resist a moment of 30.47. So that, because that is the maximum moment we are expecting at this particular depth, that is 3.68. So these are simple. If you know the basic SFT BMD things, we can solve these things. The idea is we need to know these forces and moments so that we can select these members. That is sheet pile wall, our whale beams, and our struts. So these three members we should be able to select the sections. That is the idea. Jumping to the next problem. So after braced excavation, we moved on to the next topic, that is our conduits, like is underground conduits. So when you talk about underground conduits, we should know what is a vertical pressure acting on our conduits. So in this particular case, we have a tunnel of square cross section and excavated in a sandy soil. The top of the tunnel is 5 meter below the ground level, and width of the tunnel is 6 meter. So we are supposed to find the vertical stress so that we can design the tunnel, right? So we need some cross section, some, whether it is concrete, concrete section or steel section. We should know the vertical stress acting on it. See, that's why with the tunnel lining, acting on the tunnel lining, if there is no surcharge acting on the top of the soil. So we also know the soil properties. So let us see. So here the thing is like uh, okay, but here we need to know about one formula. Okay, before that, let me just put this into perspective. Let us say this is our 6 meter, that is the width of the tunnel, and the depth of the tunnel, that is till here, it is 5 meter to the top of the tunnel. So let us say this is the tunnel. uh, we do we know this is also 6 meter, since it is a square tunnel, and we should know, so if this is 2b, what is this? This is 2b dash. So if I say this is 2b dash, I can write this as h into tan of this angle. So this angle is nothing but 45 minus 5 by 2. Since it is failing in an active failure case, it will be 45 minus 5 by 2 on both the sides. Here also it is 45 minus 5 by 2. So mm, I can write it as Here also h tan 45 minus 5 by 2. Here also h tan 45 minus 5 by 2. So I know the whole, so 2b I can write it as 2b dash is equal to 2b plus 2 into h, that is both the sides we have, that's why 2 into tan 45 minus 5 by 2. Okay, so this value is 2 into 6 plus 2 into 6 tan of 45 minus 30 by 2. This value is 12.93. So if this is beta dash, 2 beta dash, so beta dash is equal to half of this. So it will turn out to be 6.46. Let us keep it there. We also need Ka. Our Ka is 1 minus sine phi by 1 plus sine phi. If you do it for 30, we will get it as 0.5 for 30 degree. Now we have K. So why do we need K? That is the question now. So what is happening is we are trying to find the pressure acting on our tunnel, vertical pressure. This pressure's formula is derived as, so tan phi gamma b by k tan phi into 1 minus e power minus k tan phi z by b. So this z is nothing but our depth of top of our tunnel. So this equation is derived from is derived in the class. So this is derived by assuming a strip which is subjected to a vertical stress and horizontal stress, just like two-dimensional stress stress element. Uh, we can write this as k gamma w, so sigma w, sigma v. So this uh, this strip is moving down, so this shaded part is moving down, and our at the face we are resisting, so there is a shear stress. So this resistance is causing we will decrease our sigma v. So this particular element is solved, it's derived in the class, so we will end up with this particular formula. So to solve that, let us write sigma v is equal to gamma b dash by k tan phi 1 minus e power k tan phi z by b dash. So if we solve this, we will get, we know that gamma is 18. So 18 into b dash is 6.46 divided by k is 0.5 tan 30 into 1 minus e power minus 0.5 tan 30 into 5 by 6.46. If we solve this, we will get sigma v. So sigma v is, if you calculate this, you will get it as uh, sorry, I think I have made a small mistake here. K value I have made a mistake. This is nothing but 1 minus sine 30 by 1 plus sine 30. So this will be 0.5 by 1.5, that is 0.33. I made that mistake. So here instead of k it will be 0.33, and here also it will be 0.33. So if you solve this, you will get this fraction will become 610.31, 1 minus e power 1 minus 0.1488, and this will be 84.38. So that is ideal. So we get the force, the stress acting on the pressure acting, vertical pressure acting on our tunnel's upper face. So we can now design So as a if you tell the structural engineer, or if you look at the available cross sections of different linings, tunnel linings, if it is a conduit, we can find the manufactured cross section. If it is a tunnel lining, we will have to design the cross section. While designing the cross section, we will need this particular value. That is our vertical stress acting on it. So that is that. Okay. So I hope, okay, we have an option here. So 84, right? So 84 is the answer. Now, we'll before we wind up, we'll just do one more question. This question is for sewer pipe. So what's happening here is we have a rigid sewer pipe, and its diameter is given, ditch height is given, so ditch width is given. Now depth is to be covered with the depth. So backfill depth is also given as 8.53 meter. It's a clay soil backfill which weighs, so gamma is value is also given. We are supposed to find the load acting on the sewer. So this pipe, load acting on this pipe, as I told before, we need to find out, because we need that for the choosing our appropriate cross section for the pipe before we lay it. So this, for this also we have a method. So that is proposed by this Handy and Spangler. It's there in the textbook, Handy and Spangler. If you had gone through this lecture, you must have seen that our load acting on our conduit can be written as gamma BD square. So here CD is a constant, gamma is a weight, and BD is square. So what is CD? CD depends on, is a function of H by BD. This choose this CD itself, is this particular figure has to be used. So in the sense, in this particular question, our H is equal to 8.53, and our PD, that is our width of the ditch, that is given as 1.0667. So our H by BD is equal to 8.53 divided by 1.067. This turns out to be 8. So we have our this as 8. So we need to choose one of these k mu value. So we have multiple curves in this chart, and each chart is for different types of soils. For example, the first curve is, I'm not sure whether you are able to see this. The first curve is for harsh granular soils. Next is for sand gravels and saturated topsoil, and we have for maximum maximum CD for clay, and we have maximum CD for saturated clay, and we have one more for weight of the soil prism over the pipe. So I'm going to choose this particular thing, that is for clay, because we know that it's clay, and so we have this as 8. So if I'm trying to draw a line for this particular thing, I can take CD value as, this is 3.5, so I can take it as 3.3. So if I take CD as 3.3, CD is equal to 3.3, I can write the total load on the pipe as pipe is equal to CD gamma BD square. So we have 3.3 into 18.9 into 1.0668 square. So if you solve it, you will get something like 75.4 km. So this is per meter. So for each meter, it will be experiencing this value. So this is a very small problem. So I just wanted to show how to use this graph. Uh, so we will get, so it's 75. So it's okay. So that is the idea. we need to understand the relevance of these topics because it's quite important in the field. So whenever we are doing excavation and we are laying pipes or we are constructing the supports for the excavations, we should know these air pressure concepts so that we can arrive at the uh, structural requirements. So basically, what we need is which beam struts or which sheet piles to choose, or what should be the cross section of any member. So to arrive at this, we should know the details from our which is the loads, which are the loads acting on these structures. Okay, so that's all for this session. I hope things are clear. I'll be uploading this and in YouTube, and even the slides will be shared with you. Before we wind up, I just wanted to show this just to make sure you have all seen this. This is already posted uh, in our portal, and if you need any of this, you can. If you want to clarify any of the concepts in detail or practice more problems, you can go through these textbooks, and this is available in the website. Uh, so that's all for today. Feel free to post any of your doubts in the discussion forum. We'll be available. Daily we will be checking the forum, but no one, like very few people are coming up with doubts. So I would suggest you to go through this problems and solve whichever so that you can be prepared for the exam. I hope these sessions has brought more value to the course, and again, nice to be a TA with you guys. So thanks for joining. Have a nice day. If you have any doubts, please post it on discussion forum. All the best for the exam for those who are writing the exams. And yeah, so these contents will be there with you for every time. You can, for the videos, you can also, it's also available in YouTube, even our videos as well as our the NPTEL videos. uh, so okay, yeah, so thanks for joining. Have a nice day. Okay, see you.